The next important class of basic or elementary signal is what are called as sinusoidal signals or co-sinusoidal signals. This slide shows basic description of a sinusoidal signal in the co-sinusoidal form. One thing you have to be clear that sinusoidal or co-sinusoidal uh, both are treated equally in signal processing applications, because in uh, true sense there is only a 90-degree phase difference between sine and cosine. Basically, they are used to represent complex exponentials, and cosine is a real part of the complex exponential, and sine will form the imaginary part. Therefore, I can when I take the signal individually, so I can either take a sine equation or cosine equation. Accordingly, in this particular slide, I have taken cosine equation but graph I have plotted sine waveform. I mean sinusoidal waveform. It doesn't make any big difference. So general equation for a sinusoidal signal or co-sinusoidal signal is x is a function of time is equal to a cos omega t plus phi, where omega is the angular frequency, t is the time instant, and phi is the initial phase angle of the sinusoidal or co-sinusoidal wave, and a is the amplitude of the waveform. One thing you remember, a continuous time sinusoidal signal or co-sinusoidal signal which we are discussing now is always periodic. It may be of any frequency or any phase, but its periodicity is always guaranteed. That is, all sinusoidal signals and co-sinusoidal signals in the continuous time form are always periodic, and the period of the signal, that is time period, is equal to 2 pi by omega, where omega is the angular frequency. Angular frequency is normally given as 2 pi times the frequency, 2 pi. So if I write omega as 2 pi f, then 2 pi cancels, so t is equal to 1 by f, the relation between the linear frequency and time period. The relation between time period and angular frequency is t is equal to 2 pi by omega. Continuous time signals are always periodic, and proof for that is actually this equation. You can see x of t is equal to a cos omega t plus phi is a basic equation for a co-sinusoidal signal. Any signal which is periodic has a period t, and every value repeats after period t. That is, instantaneous value of a periodic signal repeats after every time period t. That is, small t is equal to t plus capital T. Let us substitute t is equal to t plus capital T, and let us see that you will get back the signal. So wherever t is there, you replace t by t plus capital T. X of t plus capital T is equal to a into cos of omega. In the place of t, I am representing t plus capital T. Then I'll open the bracket, so it becomes a cos omega t plus phi. For a continuous time periodic signal, omega t is always equal to 2 pi. Therefore, a cos omega t plus phi, because cos phi has a period of 2 pi radians. I mean, its angular period is 2 pi radians. For every 2 pi radians, cosine wave repeats. Therefore, I can write a cos omega t plus phi. That means I am getting back the original signal. That is, x of t plus t is equal to x of t. That is, after every interval of time t seconds, the same signal value repeats. So this is how graph is plotted for a sinusoidal signal. In case it is sinusoidal, the graph starts from the zero value and goes positive. In case it is a co-sinusoidal signal, graph starts from the maximum positive and starts to decrease, then go negative. That is a phase difference of 90 degrees. That is, I can say always a cosine wave leads the sine wave by 90-degree phase. These are all parameters of a sinusoidal representation: time period, amplitude, and if you represent time axis as angle, it is in terms of radian. So one full cycle is 2 pi radian, half cycle is pi radian, quarter cycle is 5 by 2 radian. If I represent the x-axis as time, then one full cycle is t seconds, then half cycle is t by 2 seconds, quarter cycle is t by 4 seconds. That means I can represent the x-axis either as a time or as a angle in radian, in representing sine or cosine graph. Okay, now what about the discrete time sinusoidal signal? That is, when I sample this continuous time signal with some sampling frequency, what happens to the discrete form representation of sinusoidal signal, that we'll see in the next slide. You can see the equation for a discrete time sinusoidal signal is x is a function of n, that is in the place of t I got n, is nothing but a cosine of omega n plus phi. So equation looks similar to the previous continuous time sinusoidal equation, with only difference that the small omega is replaced by capital omega and t is replaced by n. Wherever t is there, it is replaced by n. That is both in left hand side as well as right hand side. Now this is a discrete form of sinusoidal or cosinusoidal signal, which is obtained by sampling the continuous time sinusoidal signal. It all depends on sampling frequency selection, that is number of samples taken per cycle of the sine or cosine wave, based on which the periodicity is guaranteed. That is, a discrete time sinusoidal signal need not be periodic always. It may be or may not be periodic. It all depends on the signal condition that happens while you convert a continuous time signal into discrete time signal. The discrete time sine wave is periodic if and only if the angular frequency omega is 2 pi into n by m by n, where m and n are integers. That is, angular frequency of a periodic sinusoidal discrete time sinusoidal signal has to be the rational multiple of 2 pi radians, because n and m both are integers. That means ratio of two integers is always a rational number. So only when omega is a rational multiple of 2 pi radians. This is the condition you have to fulfill in order to make a discrete time sinusoidal signal periodic. Here m is any integer, where n is a number of samples per cycle of a if periodic discrete cosinusoidal signal. What is the proof for this formula? The proof is here. You can see, you can write the original equation of discrete time sinusoidal signal. X of n is equal to a cos omega n plus phi. In the place of n, you replace n plus capital N, where n is an integer which shows number of samples per cycle of a periodic discrete cosinusoidal signal, if at all that signal is periodic. N is the number of samples present within a cycle if the signal is periodic. So wherever n is there, replace that by n plus capital N. So on left hand side, right hand side, that is on left hand side, x of n plus capital N is equal to a into cos of omega into n plus n. You have to replace n by n plus n, then open the bracket, it will become omega n plus omega capital N plus phi. So this equation becomes periodic only if omega n is 2 pi or integer multiple of 2 pi. That is, for this signal to be periodic, the term omega into capital N must be an integer multiple of 2 pi. That is, let the integer multiple be m. That means omega n should be equal to 2 pi m. In other words, omega is equal to 2 pi m by n, where m should be an integer. So this is the condition for making sinusoidal signal to be periodic. That is, angular frequency omega must be a rational multiple of 2 pi radians. Now, how a discrete time sinusoidal signal looks like, you can see here. That is, if you take an example of a continuous time sinusoidal signal, its discrete form is this. So this signal is basically plotted by taking 24 samples. N is equal to 24. While plotting this discrete signal, you have taken 24 samples of equidistant over one cycle of sine wave. Discrete sinusoidal signal looks exactly like this. I hope this much is enough for the time being for discussing sine wave. When we discuss problems on this topic, we will discuss further few features of both continuous time and discrete time sinusoidal signals. Okay, this shows the total signal, that is both continuous time as well as discrete time sinusoidal signal of different. When I consider discrete time sinusoidal signal, you can see there are different number of samples. In all the three cases, the signal is maintained periodicity. The sampling is done in such a way that the fulfilling condition, what I said in the beginning, gets fulfilled. That is, the angular frequency of the resulting discrete time cosinusoidal signal is a rational multiple of 2 pi radians. N is selected in such a way. So signal will retain its periodicity. Next important class of signal is, it is a kind of special signal which is combination of two different signals we already studied, that is exponentially damped sinusoidal signal. Sometimes this is important part of a signal analysis when you discuss about transforms, especially Laplace transform. This plays a very important role. You can see the equation for both continuous time as well as discrete time case. A continuous time exponentially damped sinusoidal signal is given by x of t is equal to a into e to the power of minus at into sine of omega t plus phi, where alpha is greater than 0. That is, alpha is positive. You can see here this signal, that is, if I consider this as if I consider this particular part as a decreasing exponential, then the remaining part, that is this part, is a sinusoidal signal of amplitude 1. When they are multiplied, definitely the overall signal keeps on decreasing, because you are multiplying sine omega t plus phi, a sine function, with a decreasing exponential. No, the effect of decreasing exponential being multiplied to sine wave is decreasing amplitude continuously. As time progresses, amplitude decreases exponentially. So signal finally damps out. Suppose you pull a elastic body, then leave it on its own. If you just strike a elastic body and just suppose you stretch an elastic body, then if you release it, the vibrations that happens are nothing but damped sine waves. That is, signal finally, I mean, the vibrating body comes to rest after some interval of time. So example of a decreasing exponentially damped sinusoidal signal. Similarly, for a discrete time case, the same exponentially damped sinusoidal signal can be written as x of n. X of n is equal to b into r to the power of n sine of omega n plus phi. Once again, the amplitude of the discrete time sinusoidal signal is a decreasing exponential whenever the mod of r is between 0 and 1. That means r can be positive or negative, but its modulus must be, that is, its magnitude must be a fraction. That is, r must be a fraction, either positive or negative. In both cases, you will get the decreasing, that is exponentially decreasing or exponentially damped sinusoidal signal. So the two signals shown are, the equations shown are examples of multiplication of a damped exponential with a sine function. Only graph has been shown for continuous time signal. Similarly, we can draw the graph for discrete time signal, counterpart of exponentially damped sinusoidal signal. Next very important class of signal is step function. What is a step function? The basic definition and graphical representation of a unit step function has been shown here for a continuous time case. You can see there is one step, a sudden change, abrupt change from value of the signal, and then change. After that change, the signal remain constant. You can see the unit step signal, that is step function, is normally defined by, normally denoted by the notation u. U stands for unit. U of t means unit step. For a normal unit step function, the signal change occurs at origin, that is t is equal to 0. The signal changes by 1. By default, the signal becomes 1. From 0, it becomes 1 in no time. Then that 1 remains constant throughout the signal interval. That is, as long as signal lasts, the value remains constant 1. So there is a change, abrupt change only at the origin, and the change happens in 0 seconds. That is, signal changes from 0 to 1 in 0 seconds. So it's only a theoretical abstraction, because in practice nothing can change 0 time. It will always take some finite time. But theoretically speaking, you can always imagine a signal changing value from one to another in 0 seconds, only theoretically. So for all the values of t less than 0, the signal value is 0. For all the values of t greater than 0, signal value is 1. Hence, the equation for a unit step function in continuous time mode is given by u of t is equal to 1 for t greater than 0. I think a modification has been made, a small modification. I'll write it as like this: t greater than or equal to, I'll write it like this. See, for t greater than or equal to 0, the signal is 1. Because at t is equal to 0, the signal changes to 1, no? If you ask me what is the value of signal at t is equal to 0, that is u at 0, what? It is actually 1. Therefore, I can include this value as also. That is, for t greater than or equal to 0, the signal is 1. For all the value of t less than 0, signal is 0. And signal changes value at t is equal to 0. So you can see, if you ask me what is the value of signal at t is equal to 0, I can say 0 as well as all other values up to 1. All these values are happening at t is equal to 0. Now you may be confused because there are multiple values at t is equal to 0. No, I can always mark two things. One is 0 minus 0 to the power of minus. Then here, this instant, I can mark always as 0 to the power of plus. 0 to the power of plus. Now I can say u at 0 minus is 0, u at 0 plus is 1. Sometimes this kind of representation is required in some signal analysis. That is, u at 0 minus is equal to 0. Once again, u at 0 minus is equal to is equal to 0. Then u at 0 plus is equal to 1. I think it has gone out of the screen, whatever I wrote. Let us once again write here. U at 0 minus, I'm sorry, this pen I'm not able to write. Okay, I'll explain here itself. U at 0 minus is equal to 0. U at 0 plus is equal to 1. That is, u at 0 minus means this instant, u at 0 plus is this instant. This is t is equal to 0 minus, this is t is equal to 0 plus. Sometimes this will help us in some signal analysis because the signal is changing too fast. At t is equal to 0, it is changing from 0 to 1. Therefore, this way also you can look at the signal. Anyway, there is one change that occurs at t is equal to 0, and that is, if it is by value 1, it is called unit change, or the signal is said to be unit step signal. This is a description of a continuous time unit step signal, or simply a step function. Then what about the discrete time case, that is discrete time step signal? It is exactly this. It is quite straightforward. As you can see, it is a sampled version of the above signal. So x of n is equal to, or to be more precise, u of n, because it is a unit step signal. No? Therefore, u of n is equal to 1 for all the values of n equal to and greater than 0. U of n is equal to 0 for all the values of n less than 0. That is, for all values of n less than 0, the signal values are 0. The signal changes at n is equal to 0, isn't it? Its value becomes 1, then remains 1 till n is equal to infinity. Therefore, it is easy to write the equation for a discrete time unit step signal. U of n is equal to 1 for n greater than or equal to 0, u of n is equal to 0 for all the values of n less than 0. This is the discrete time equation, equation as well as signal graph for a unit step signal. We have discussed two basic signals in this part, that is exponentially damped sine signal, sine function, both continuous time and discrete time, as well as step function, both continuous time and discrete time. Let us end this part 4. Let us come to, let us move to next part to continue discussing remaining types of basic signals.